Hello, my name is Todd Arnold. I recently completed my PhD underneath Katz-Bassett at Columbia University, and I'm now a research scientist and assistant professor at the U.S. Military Academy at West Point. The major cloud providers have some of the largest networks on the internet. They're highly interconnected with other autonomous systems, and an increasing number of online services rely on the cloud providers' infrastructures. The major cloud providers are some of the most important networks on the internet. However, traditional methods to assess and identify influential networks in the internet's topology miss all of the diverse connectivity enabled by flattening. In this work, we examine the impact of cloud providers' hidden interconnectivity and how they have formed almost an alternate internet backbone in the flattened internet. The traditional view of the internet is a tiered hierarchical topology with lower tiers being edge networks, such as user, enterprise, and content provider networks. The upper tiers are internet service providers of various sizes. The ISPs interconnect with edge networks, so the edge networks can exchange traffic with each other. At the apex are the Tier-1 ISPs, 12 to 20 global networks that all interconnect with each other and ensure the internet's global reachability property, which means any source can reach any destination. For the networks to exchange traffic, they have to pay the higher tiers for the interconnection, and they pay as a function of the amount of traffic exchanged. Transporting the traffic for external networks is known as transit. We can see multiple networks of each type in the graph on the right. If a user in ISP2 wants to access the cloud, it would have a long, circuitous path to reach it. Now, internet flattening is an effort to shorten the paths between networks with more direct connectivity and to bypass the upper levels of the hierarchy. For example, the networks could add new interconnects, highlighted in blue, to establish direct connectivity, which would shorten the paths between the cloud provider and the user ISPs. If we look at user ISP2 and the cloud once again, we can see they are now directly connected. These interconnects are one effort that the cloud and other content providers have been pursuing for the past 10 years. The direct connectivity increases route diversity, leading to more control over routing decisions and control over a larger fraction of the path between a user and hosted content, which in turn improves performance. Internet flattening has fundamentally altered the paths that most traffic takes between services and end-user networks. Many estimates believe that the majority of traffic now occurs across these direct interconnects. However, the impact of this flattening is not captured by traditional approaches. The direct interconnects are invisible to traditional monitoring and measurement efforts. Existing metrics of importance, such as customer count, focus on how much transit an autonomous system could provide based on its place in the topology, rather than on what transit it does provide, and does not reflect the rich peering interconnectivity of the flattened internet. Combined, this means that the most used internet topologies are missing most links used by these hugely important cloud providers, and the value of the most used metrics do not actually change as flattening increases. Our goal is to understand this gap and capture the progress of internet flattening. We want to first uncover these missing links, and second, to understand to what degree they enable cloud providers to bypass the traditional hierarchy. This will allow us to capture the progress of flattening, understand how much these cloud routes have gone hidden from the traditional approaches, and to understand the degree to which the cloud providers now represent almost an alternate internet backbone. We need a method to determine the cloud provider's connectivity and to realistically model the paths between the cloud providers and users. Two common techniques to identify network interconnectivity are BGP feeds and trace routes. However, they both have inherent limitations. First, both are biased by the number and location of observation points. Specifically for BGP, it has a good view of the hierarchical internet, with past studies showing that public BGP feeds have visibility of over 90% of Tier-1 and Tier-2 interconnections. However, its coverage is quite poor for edge networks and peering links, both of which apply to the cloud providers, having visibility into only 10% of those interconnections. Trace routes can be sourced from inside the cloud providers, so they'll have a much better visibility into the cloud's interconnectivity. However, trace routes can infer false links in a number of scenarios, such as drop packets or load balancing. Further complicating the issue is that the cloud providers could potentially interfere with measurements. Finally, there are virtual links to the cloud providers that are not visible even from inside the cloud. And this last problem is an open question. Despite their limitations, both measurements are extremely useful and have their benefits. BGP can see a high percentage of the hierarchical links, while traceroute can reveal much of the direct connectivity of the clouds. To perform our analysis, we use both data sources, which allows us to leverage their beneficial aspects while reducing the impacts of their limitations. So in order to determine which networks the cloud providers are able to exchange traffic with when bypassing the internet hierarchy, we use both sources to construct an autonomous system level topology graph of the internet. We start with the K to AS relationship dataset, specifically the one for September 2020, which comes from public BGP feeds as the basis for internet topology. But based on the shortfalls of BGP feeds, as we mentioned earlier, we know that we'll not have sufficient coverage of the cloud providers' networks. The dataset we use also incorporates trace routes from Kata's archipelago probes, but none of the probes are located inside the cloud provider networks. So we augment this topology with neighbors we identify in trace routes. We use trace routes to identify neighbors of the cloud providers that we can then add into the autonomous system topology graph. We identify neighbors that we source from trace routes from VMs inside the cloud providers using Scamper and ICMP probes. And we measured all prefixes. Accurately mapping the IP addresses in the trace routes to identify autonomous system neighbors is a critical step. So we make several attempts to identify the correct IP to autonomous system number. Consider the simple topology on the right, where there are potentially 6 hops in our trace route, one for each router and the final destination. Now in this scenario, this is what our trace route, as shown by the red line, could return. We have a single timeout, then 5 hops to reach our destination. We then need to map the IP addresses to autonomous system numbers. Our preference for resolving IP addresses to autonomous system numbers is to use peering DB, then SIMRU, and finally who is information. If none of these resolves an IP to an autonomous system number, we cannot resolve it. Using our sources, we can see that 3 different autonomous systems are associated with the hops. A cloud provider hop, in this case 8075, which is Microsoft, then autonomous system 24753, and 11127. For traceroute to be considered valid in our dataset, we require the traceroute to have at least one cloud IP address resolved to its autonomous system number, and one non-cloud hop resolve. And there can be no intermediate hop between the last cloud hop and the first non-cloud hop, which right now, there are no gaps, so this is a valid traceroute, and we identify 24753 as a neighbor of Microsoft. If we had a timeout from the intermediate network router in the third hop, we would be unable to use this traceroute because it has an intermediate unresolved hop between the cloud provider and the next resolved autonomous system. We use our traceroute dataset only to determine cloud provider neighbors. We do not add other discovered links into the topology to prevent traceroute's limitations from impacting our analysis. Now, some of you may hone in on the steps we take to resolve IPs to autonomous system numbers, specifically using peering DB and whois data. And we'll explain our reasoning momentarily, since these choices are deliberate, and we'll show that these steps make a significant difference in accurately identifying cloud provider neighbors. The key results of our paper rely heavily on accurately identifying the neighbors of the cloud providers. So we reached out to all 4 that we examined, and we received feedback from Microsoft and Google. Both Microsoft and Google provided us with feedback on the true and false positives, which is whether autonomous systems we identified as neighbors are actual neighbors or not, which we use to calculate a false discovery rate, which is false positives divided by false positives plus true positives. They also provided a false and true negatives, whether autonomous systems we identified as not neighbors are actual neighbors or not, allowing us to determine a false negative rate, or false negatives divided by false negatives plus true positives. We were able to iterate over our results with the cloud providers to determine the impact on accuracy as we refined our methodology. Microsoft was able to provide us with a slightly more detailed feedback, so we worked more closely with them to refine our neighbor identification methodology. We would then apply the updated methods to our data sets, and Google was able to validate that our refinements improved our identification accuracy. The numbers presented during our walkthrough in terms of false discovery rate, false negative rate, and neighbors are our results for Microsoft, with the final results for Google included. Our regional neighbor identification methodology allowed a single unresponsive hop between the last identified cloud provider hop and the first non-cloud provider hop. So in a traceroute, we allowed an intermediate hop and assumed that the first non-cloud hop indicated a neighbor. When we provided our neighbor sets to the cloud providers, we discovered that the first sets of neighbors were pretty far off, with approximately a 50% false discovery rate and 23 to 50% false negative rate. We identified a little over 8,900 neighbors for Microsoft and over 13,000 for Google. Based on the feedback, we examined examples of false positives and discovered most had an intermediate hop between the cloud provider and the next resolved autonomous system, invalidating that assumption. Occasionally, this was a timeout, which means we cannot do anything further and have to discard the traceroute. More frequently, it was actually an IP address that was not resolved to an autonomous system. So we discovered that most of these occurrences were for valid IP space, which is allocated to networks and registered in WHOIS, but are not advertised in BGP, which is why SIMRU cannot resolve them. In many cases, the WHOIS information pointed to ISPs. So digging further, we found that PeeringDB contained mappings for many of these IP addresses, which meant that the IPs were registered to ISP member networks. We used PeeringDB to resolve these IP addresses. As we can see here, the previously unresolved IP is actually used by Globecom AS24753 at the Neutral Internet Exchange. So by using PeeringDB and not allowing an intermediate unresolved hop, we reduced our false discovery rate and false negative rates significantly and identified nearly 3,000 neighbors of Microsoft. An additional source of false negatives we were informed of was that the cloud providers have peers at certain locations that are only used for traffic at those locations. To try and reduce false negatives, we expanded the number of locations we measured from to capture these potential neighbors that fell into this category. This reduced our false discovery rate, but in turn reduced our false negative rate, but in turn increased our false discovery rates. And we were able to identify a little over 3,600 neighbors for Microsoft. We investigated further to determine whether we could improve our accuracy. When we look at IP addresses that were resolved by SIMRU but appeared in PeeringDB, this showed a number of trace routes that traversed a network that belonged to an ISP and was announced in BGP, but PeeringDB had more specific resolution to an individual autonomous system at the ISP. So we preferred the PeeringDB resolution, resulting in a false discovery rate of 11% and false negative rate of 21% for Microsoft. And we discovered 3,565 neighbors. Google had a false discovery rate of 15%, a similar false negative rate to that of Microsoft. And we identified 7,554 neighbors. Armed with an accurate set of neighbors for the cloud providers and an updated AS level topology, we sought to quantify the potential of the cloud providers to bypass the internet hierarchy. Customer cone would tell us who is reachable through customer links, but that misses all of the connectivity enabled by the rich peering we see with flattening. Plus, cloud providers typically do not have customers or customer cones. So instead, we're going to look at who is reachable through an autonomous system peers as well. Essentially, it's peering cone. This will reach any networks that are not only reachable through transit providers. We're going to restrict it a little bit more and not consider routes through Tier-1 and Tier-2 peers, since those peers would provide access to the traditional hierarchy. We define reachability from the perspective of an autonomous system making a prefix announcement, which we call the origin. Now, any network that receives the announcement made by the origin is considered reachable by the origin. We make the announcement using our augmented AS topology graph and enforce common routing policies such as valid free, preferring peer over provider, and customer over peer. If we walk through an example using the graph on the right, we set the cloud as the origin, which is the AS making the announcement, and the network for which we're calculating reachability. Currently, the reachability for any network without restricting propagation is 7, because all networks can exchange traffic. Since we're not propagating routes through providers, we do not propagate announcements to ISP-B and the regional transit, which removes them from the cloud's reachability. Next, we restrict Tier 1 peers, which also removes ISP-A. Finally, we restrict the Tier 2 peers from propagating routes, which removes ISP-C and ISP-1. So when the cloud announces a prefix, only ISP-2 and 3 receive the announcement. So they're the only autonomous systems reachable from the cloud, making the cloud providers reachability 2 in this scenario. We define the total number of reachable autonomous systems when not traversing any of the aforementioned networks as hierarchy for reachability of the origin. So we calculated hierarchy for reachability for the cloud providers, Tier 1s and Tier 2s. We compared the calculated reachability of the cloud providers to those of the Tier 1 and Tier 2 ISPs because they're the networks the cloud providers are trying to bypass and are the measuring stick against which other networks are frequently compared. The graph shows the reachability calculations for the cloud providers, Tier 1 and Tier 2 ISPs. The x-axis is the different provider networks sorted according to reachability. The y-axis is the reachability count of destination networks out of all autonomous systems on the internet, which totals 69,488 autonomous systems. Each bar represents the individual provider's reachability without traversing Tier 1 or Tier 2 ISPs or their individual provider networks. Cloud providers are in blue, Tier 1 in red, and Tier 2 in green. We can see that the cloud providers are 3 of the top 5 networks, ranked by reachability, with Google holding the number 3 position, virtually the same as Hurricane Electric, which is a Tier 2. The Tier 1s are scattered throughout the graph, including several of the top networks and some of the lowest. This shows that some Tier 1s are pursuing connectivity outside the group of Tier 1s more aggressively than others. But nearly all of them can reach at least half of the internet independently of the other Tier 1s and Tier 2s. The Tier 2s are mostly concentrated around the middle, with the exception of Hurricane Electric, which is in the number 2 position. Unlike most Tier 1s, which are highly selective about their peering agreements, Hurricane Electric has an open peering policy and will peer with any network that is also at a facility where Hurricane Electric has a presence, in addition to selling the transit services. So we can see that the cloud provider's peering strategy enables them to reach their network, most networks, without traversing the Tier 1 and Tier 2 or their individual transit provider networks. In the paper, we also analyze the reachability for all networks and show that while the top networks remain the same, there are thousands of networks which are also able to reach a sizable portion of the internet without traversing the internet hierarchy. We examine how reachability has changed over time, comparing our results for reachability against those from September 2015, showing that Google has had high reachability for the past 5 years, but the other cloud providers have increased significantly during that time. We also examine the implications of the increased interconnectivity and how the increased reachability provides some level of protection against routing attacks. So in conclusion, we emulated the connectivity of the cloud providers based on multiple sources of data, including validated neighbor sets from the 2 of the cloud providers that we examined. We developed hierarchy-free reachability, which quantifies the extent to which a network can reach other networks when bypassing the traditional hierarchical internet. And hierarchy-free reachability shows that there are thousands of networks which are also able to reach a large portion of the internet without traversing the hierarchy, an insight that is not captured in other metrics which seek to measure network's importance. Chief amongst these are the cloud providers, which are better able to reach a vast majority of networks and are amongst the top networks on the internet from this perspective. As the internet's topology and traffic patterns continue to shift, we should continue to explore additional methods and metrics to determine the influence of individual autonomous systems. Thank you.